Welcome to my presentation on transmission line theory. Myself, Anand Selvakarthik, Assistant Professor, Department of ECE, Hindustan College of Engineering and Technology. Outline. The outlines are transmission line theory, basic transmission line, characteristic impedance, propagation constant, lossless condition, followed by limitation of transmission line. The transmission line theory. First of all, what is the need? Whenever the length of the line is significant when compared to its wavelength. The next is basic transmission line model. Here you can see two conductors. This is inner conductor, the other is outer conductor, or else two conductors parallelly kept with finite distance of, equal distance of separation. We can call this as a basic model of a transmission line. The parameters are capacitance, inductance, resistance, and conductance. And in this slide, we'll be seeing how we are getting inductance effect as well as capacitance effect. You can see here the diameter of each conductor and the spacing between them. Let it be a dielectric. As a whole, we'll be getting a capacitance effect based on the diameter as well as the dielectric medium exists between these two conductors is capable of producing capacitance effect, whereas the length of this particular transmission line constitute the inductance effect. Based on this, we are obtaining inductance as well as capacitance, and this is what the equivalent circuit model of transmission line. Characteristic impedance. This is what one of the important parameter of a transmission line as sender, and this will be the line, and this is load. But the line impedance is called as the characteristic impedance Z0, whereas the load impedance is ZL. It should be equal for a lossless condition. We all know Z equal to R plus J omega L and Y equal to G plus J omega C. Based on that, we are formulating Z0, which is equal to root of Z by Y. It can be written in terms of RLGC. The next important parameter is propagation constant, which is denoted by gamma. Gamma is basically which is equal to alpha plus J beta, where alpha is attenuation constant, beta is phase constant. And we can also written this gamma as root of Zy, and we can replace this Z by R plus J omega L and Y by G plus J omega C. Lossless condition. The lossless condition are R equal to 0, G equal to 0, the other is alpha equal to 0. Based on the equations, if it consists of RLGC, I can prefer this R equal to 0 and G equal to 0. And if it is based on propagation constant, I can go with this alpha. Based on these conditions, I can state the expression as a lossless one based by substituting these two conditions. Based on this, I am getting Z0 equal to root of L by C, whereas phase velocity equal to 1 by root LC. The important thing is it is independent of frequency. Then only you can call it as a lossless condition. The other is based on the medium. As I said, two conductors. In between is a dielectric medium. It may be of any medium, mu or epsilon. So based on this, we are formulating the lossless condition, that is LC equal to mu epsilon. And based on this, we are obtaining beta equal to omega into root LC, and which is equal to omega into root of mu epsilon. And in the lossless case, the phase velocity does not depend on the frequency, and it is always equal to the speed of light. So as a whole, if we are assuming it as a lossless one, it should not depend on frequency. The next is limitations of transmission line. A discontinuity on the twin lead will cause radiation to occur. In simple words, if there is any bend or twist in the transmission line, definitely there will be a loss, and we'll be calling it as a reflection. And the notice radiation effects usually increases as the frequency increases. So that's all about transmission line theory. Thanks for watching my presentation.